When dealing with long feeder runs, particularly those involving parallel conductors, understanding the requirements of NEC section 250.122 is crucial for ensuring safety and code compliance. Let's analyze a scenario involving a 2000 amp 480/277 volts feed from a 4000 amp main service switchboard to a 2000 amp switchboard, spanning over 1000 feet. To mitigate voltage drop, the design employs 10 4-inch conduits, each containing 4 600 kcmil conductors. The primary question revolves around the appropriate sizing of the grounding electrode conductors within these conduits, specifically concerning section 250.122 paragraphs F1 and B. The initial concern stems from the interpretation of table 250.122, which suggests a 250 kcmil grounding electrode conductor for a 2000 amp device. Given the parallel nature of the conductors, the question arises whether the grounding electrode conductors need to be upsized proportionally. Paragraph 250.122 F1 addresses scenarios where a feeder supplies multiple branch circuits. It stipulates that the neutral conductor must have an ampacity not less than the sum of the ampacities of the supply branch circuit neutral conductors. In this particular setup, each of the 10 parallel 4-inch conduits contains 4 600 kcmil conductors. The ampacity of each ungrounded conductor is determined by its size and insulation type, typically found in NEC Table 310.15. Assuming a standard insulation type such as THHN, a 600 kcmil copper conductor has an ampacity of approximately 475 amps. Therefore, the total ampacity of the ungrounded conductors in each conduit is 4 times 475 amps, equaling 1900 amps per conduit. Now, let's examine the grounding electrode conductor requirements. Table 250.122 indeed indicates a 250 kcmil copper conductor for a 2000 amp overcurrent protective device. The key point is to understand how this requirement applies in the context of parallel conductors. The code recognizes that when conductors are run in parallel, the grounding electrode conductor also needs to be run in parallel. However, the size of the grounding electrode conductor in each conduit does not necessarily need to be the same size as if it were serving the entire 2000 amp load on its own. Instead, it needs to be sized appropriately for the portion of the load it serves. To determine the required size, consider the ampacity of the conductors within each conduit. As previously established, each conduit carries 1900 amps of ungrounded conductors. Therefore, the grounding electrode conductor within each conduit must be sized according to Table 250.122 based on this 1900 amp value, not the total 2000 amp value. Referring to Table 250.122, a 250 kcmil copper grounding electrode conductor is suitable for a 2000 amp service. However, since each conduit only carries 1900 amps, a smaller grounding electrode conductor may be permissible, provided it meets the requirements of the table for that ampacity. For example, a 1/0 AWG copper conductor is typically rated for 150 amps, which may be sufficient for a 1900 amp load, depending on the specific installation conditions and any applicable dirting factors. The critical point is to ensure that the grounding electrode conductor within each conduit is adequately sized to handle the fault current that it may be subjected to. This requires careful consideration of the available fault current at the source, the impedance of the conductors, and the clearing time of the overcurrent protective devices. Now, let's address the second question regarding ground fault protection. Section 250.122 F2 discusses the use of ground fault protection to reduce the size of the grounding electrode conductor. However, this provision typically applies to services, not feeders. In the scenario presented, the 2000 amp feed is a feeder, not a service. Therefore, the provisions of 250.122 F2 do not directly apply. Nevertheless, ground fault protection can still be a valuable addition to the system. While it may not allow for a reduction in the size of the grounding electrode conductors, it can provide enhanced protection against ground faults, reducing the risk of equipment damage and electrical hazards. Ground fault protection works by detecting imbalances in the current flowing through the ungrounded conductors and the neutral conductor. When a ground fault occurs, a portion of the current flows through the grounding path, creating an imbalance. The ground fault protection system senses this imbalance and trips the overcurrent protective device, interrupting the flow of current and clearing the fault. The installation of ground fault protection on the 2000 amp branch breaker at the main switchboard can significantly improve the safety and reliability of the system. It can also help to reduce the risk of arc flash events, which can be extremely dangerous. In summary, when dealing with parallel conductors in a long feeder run, the grounding electrode conductor must be sized appropriately for the portion of the load it serves. Table 250.122 should be used as a guide, but careful consideration must be given to the ampacity of the conductors within each conduit and the available fault current. While ground fault protection is not required in this scenario to reduce the size of the grounding electrode conductors, it can be a valuable addition to the system, providing enhanced protection against ground faults and reducing the risk of electrical hazards. Remember to always consult with a qualified electrical engineer and adhere to all applicable codes and standards when designing and installing electrical systems. It's also important to note that the specific requirements for grounding and bonding can vary depending on the local jurisdiction and the specific application. Therefore, it is always best to consult with the local authority having jurisdiction to ensure compliance. In addition to the requirements of Section 250.122, there may be other applicable requirements in the NEC that need to be considered. For example, Section 250.4a.5 requires that the grounding electrode conductor be connected to the grounding electrode system of the service. This ensures that the electrical system is properly grounded and bonded to the earth, providing a low impedance path for fault current to flow back to the source. Section 250.64 also contains requirements for the installation of grounding electrode conductors. These requirements include provisions for the size, material, and routing of the grounding electrode conductor. It is important to follow these requirements carefully to ensure that the grounding electrode conductor is properly installed and provides a reliable grounding path. When dealing with long feeder runs, it is also important to consider the effects of voltage drop. Voltage drop can occur when the voltage at the load is less than the voltage at the source. This can be caused by the resistance of the conductors and the length of the run. To minimize voltage drop, it is important to use conductors that are large enough to carry the load current without excessive voltage drop. The NEC provides guidelines for calculating voltage drop in Section 215.2b. These guidelines can be used to determine the appropriate conductor size for a given load and run length. In addition to conductor size, other factors can also affect voltage drop, such as the type of conductor material, the insulation type, and the ambient temperature. It is important to consider these factors when calculating voltage drop to ensure that the voltage at the load is within acceptable limits. When dealing with parallel conductors, it is also important to ensure that the conductors are properly balanced. This means that each conductor should carry an equal share of the load current. If the conductors are not balanced, one conductor may be overloaded, while the other conductors are underloaded. This can lead to overheating and premature failure of the conductors. To ensure that the conductors are properly balanced, it is important to use conductors that are of the same size, material, and length. The conductors should also be installed in close proximity to each other to minimize the effects of inductance. In addition to the grounding electrode conductor, it is also important to ensure that the equipment grounding conductors are properly sized and installed. Equipment grounding conductors provide a path for fault current to flow back to the source in the event of a ground fault. The size of the equipment grounding conductor is determined by Table 250.122 based on the size of the overcurrent protective device protecting the circuit. The equipment grounding conductor must be installed in the same raceway or cable as the circuit conductors. It must also be connected to all metal enclosures and equipment that are likely to become energized in the event of a ground fault. In addition to the requirements of the NEC, there may be other applicable codes and standards that need to be considered. For example, the National Electrical Safety Code or NESC, provides guidelines for the design, installation, and maintenance of electrical power and communication systems. The NESC is often used by utilities and other organizations that operate electrical power systems. It is important to consult with a qualified electrical engineer and adhere to all applicable codes and standards when designing and installing electrical systems to ensure safety and compliance. It's important to remember that electrical codes and standards are constantly evolving to reflect new technologies and safety concerns. Therefore, it is essential to stay up to date on the latest requirements to ensure that your electrical systems are safe and compliant. Continuing education courses and professional organizations can provide valuable resources for staying informed about changes to electrical codes and standards. They offer opportunities to learn from experts, network with other professionals, and gain a deeper understanding of the complex issues involved in electrical system design and installation. By investing in continuing education, you can demonstrate your commitment to safety and quality and enhance your professional skills. In summary, designing and installing electrical systems for long feeder runs with parallel conductors requires careful attention to detail and a thorough understanding of the applicable codes and standards. By following the guidelines outlined in the NEC and consulting with qualified professionals, you can ensure that your electrical systems are safe, reliable, and compliant with all applicable regulations. The use of appropriate grounding and bonding techniques, proper conductor sizing, and ground fault protection can significantly reduce the risk of electrical hazards and improve the overall performance of your electrical systems. Always prioritize safety and seek expert advice when necessary to ensure the well-being of yourself and others.